Alright, so what I've done is draw some magnificent structures on the board, as you can see. Matt, look, I'll put all this effort into this. And so we're moving on with the section on silicates, quite obviously, because that's what it says. Where have we come across silicates before in the course?
Toxic cations in soil.
Good. Okay. When we talked about acid rain, if you can go right back to that topic, we spoke about the issue with aluminium being released into the soil, and we used that definition of cation exchange. And we said there were silicate structures in the soil, and the silicate structures are actually soil, dirt. It's the minerals that we find in all soil. And we said they were negatively charged. And we said attracted to the surface of these minerals, funny enough, okay, are metallic ions. So that's where this links into the course. You can see a lot of stuff in the Year 12 course sort of connects, all right? So we spoke about that earlier in the year when we talked about releasing metal ions into the soil. And the one we were worried about when we did that was the aluminium, because we know that aluminium affects the ability for plants to resist attacks from bugs and viruses and so on. Now, we did it there. Where else did we talk about silicates? Yeah, we use silicate, right, as a polar stationary phase, all right, in chromatography. Thanks, Mason. I didn't even think about that one. So there's actually another place, all right? So I forgot about the fact that we use silicates as a stationary phase, as an example of a polar stationary phase for chromatography in TLC or column chromatography, all right? Where else do we use it? Silicates we've spoken about before. Give you a hint. We use the word, okay, when we talked about it, we use the word clay. Flocculation. Is that what you said?
Yes.
Good. Okay. You said something else then. So we use the word flocculation when we spoke about a potable water supply. What was the problem with clay particles? They were, Jack? They're too small, okay, and so we couldn't actually filter them out, and they're all negatively charged on their surface, so didn't matter what we did, we couldn't get them to come together, okay? So we added a flocculating agent, it was one of the test questions, and we added aluminium sulfate, yeah, all right, or any other aluminium salt, okay, because the aluminium allowed the clay to stick to it, formed a precipitate, and it took the clay out of the dirty water to make it sort of drinkable, potable. So we had done it before, all right? So now we're just going to get into the structure of silicates, but there's a limit to how far you need to go with silicate structures. The first thing to understand is that all minerals, all silicate minerals, every time you go digging in the soil, they're really based on one simple structure, and they're based on a simple SiO4 minus 4 tetrahedra. That's what they're all based on, okay? And so if you can use Lego, can anybody use Lego, like build up things? Good, excellent. If you can use Lego, you can build silicate structures, as you can see. This is not Lego, but this is my Lego, if you're a chemist, all right? So we can build up structures based on the SiO4 tetrahedra. All right, there are 6 structures of silicate, 6 groups of structures of silicates that you're going to need to know. You can either learn them, learn all these formulas if you have the capacity to do that, okay? Or for at least 4, these first 4, you can sort of work those out. And I'll explain how you can work out the structure for the first 4. First one's simple, okay? SiO4 minus 4. So you should be able to work out the structure of this particular silicate because it's the simplest one. The formula is going to be SiO4 minus 4. So when we put it into a silicate structure like phosphorite, now you don't need to know any of these names, okay? You don't need to know the name, but what you do need to know is what group of silicates this comes from. And I'll add some names to these in a minute, okay? So these are simply the group that's looking at single tetrahedra. They're the simplest ones. Okay? Now, how do I know that? Well, you should be able to look at the silicate structure and work out the SiO4 simple, more or less. Okay? So the SiO4 structure is what we're looking at when we're talking about single tetrahedra. So if I come across a formula like this, okay, I need to identify that part of the formula. I've got to separate out the metal ions from the silicate part of the structure. One thing I haven't mentioned yet is aluminosilicates. Aluminosilicates, all right, we need to be aware of them, but we don't need to be able to draw the structures for aluminosilicates. Because an aluminosilicate basically is a silicate where we take a silicon out and we put an aluminium in. And that changes things, and I'll talk about that in a minute if somebody reminds me of that one. All right, so this is based on this SiO4 single tetrahedra. So I've learnt this, and so I can pick that out in the formula. What they will ask you to do, okay, there'll be 1 or 2 marks in the exam, is they might just say, all right, if I've got SiO4, and if I give you a couple of cations, let's assume if I gave you, say, calcium, and if I give you sodium, okay, the question is, how could I form a mineral structure using calcium and sodium ions? Any idea? They would have to have a -3. No.
You have to be Ca2.
How many positive charges do I need to have in total? There's a couple of ways we can look at it. I need to have 4, don't I? Okay? Because if I put a line down there, the total over there is -4. We know SiO4 -4 because I've learned that up over here. Okay? So the total of all the positive charges has to come up to be +4. So it'll be like CaNa2 SiO4 in order to make that structure work. Alright? What about if I doubled the calcium, had 2 calciums? That would be +4, +5. No, that's not going to work. Calcium by itself? +2, +1? No.
No, as in without.
Just Ca2. That's it.
No, you can't, because I'm telling you that these 2 things are in this mineral, whatever the mineral is.
The mineral can't have numerical charge.
No, it can't. This is a salt. This is just like we going right back to basics, stage 1, all right? When we were doing formulas like sodium chloride, okay, and magnesium chloride, you know, we had to have a neutral ionic structure. Same rules apply. Just a little bit complex this time, though, because we're dealing with lots of metal ions and a very complex anion in terms of silicate structure. So you've got to be able to balance those things out. And hopefully you can see that we've got 2 magnesium here at +2. Well, obviously that works already. So you need to be able to actually work backwards and work out structures of metal ions, okay, in a silicate formula. It's just a complex ionic formula at the end of the day. And I'll show you work on these individually later. There's a few little questions to look at.
Mr. Campbell,
Ah, yes.
can there be more than one metal ion? Like, can be calcium as well?
Yeah, I could actually throw, when you say I could have calcium, sodium, and magnesium.
It can be doesn't need to be one metal ion.
It does need to be 1. If it's 1, it's simple. If it's 2, it's slightly more complex. David? Yeah, you can have 2 NAs. Yeah, it'd be Na2, not Na +2. 2 sodiums. Yeah, that would work. And that's the only way we can balance this formula. So that would be the formula, all right, for that structure. If I told you that calcium and sodium were part of that mineral formula, okay, that's the only way you can do it. All right. So just as a side, that's also something that we need to be able to do. All right, so you've got to be able to work out the charges on these, okay, structures, but also you have to work out what family of silicates it comes from and be able to work backwards, okay? And we're talking about here single tetrahedra, all right? This one here has got 2 SiO4s side by side, and here it is, okay? So again, I don't think these are too difficult to work out. 1, 2, Si2. 1, 2, 3, 4, 5, 6, 7. So there's 7 oxygens. This one's accounted for, so it's 1, 2, 3, 4, 5, 6 negatives. So Si2O7 negative 6, okay, is what we should get for that structure. All right, this one here. So that's just simply what we call double tetrahedra. Okay, so 2. How do I know it is a double tetrahedra type silicate? Because I'm looking for the Si2O7 somewhere in the structure. And as soon as I see Si2O7, okay, that's going to come up to be -6 as the charge on that. Okay? Now, the charge on hydroxide is negative. Okay? The charge on water is nothing. Why is the water sitting there for? It is what? No. It's not aqueous. No. No, it's not condensation. We've seen this before. So somewhere in this structure, okay, not just one of these, there's heaps of these things obviously that make up the crystal structure. Trapped in there, there's a water molecule for every one of these. That's all it means. Okay? So it's a hydrated form of this crystal structure. That's all it means. Alright? Copper sulfate is what colour? Blue. Alright? And actually there's two versions of copper sulfate. There's copper sulfate anhydrous, which is that one, which is white. And there is copper sulfate that we actually draw it like this. 5 water molecules. That's the hydrated version of copper sulfate. We heat copper sulfate, we can turn it into blue, from the blue colour, so that's actually blue, and this stuff over here is white, but it automatically absorbs moisture from the atmosphere. Okay? It's hygroscopic. Most crystalline substances are. They're like a sponge for water. Alright, so this one here is hemimorphite, don't need to know the name. Got to pick out the structure of the silicate.
Si2O7? Yes.
What?
Si2?
Oh yeah, sorry, thanks. Si2 might be better. Yeah. Si2 has got to correspond to that structure over there. Alright, now, again, if we total up the negatives, the negative charges, alright, for this structure, we find hopefully that it's got -6 here. And there's 2 -2, so we've got -8. Zn has got a charge of +2, so we've got +8. Okay, so hopefully, logically, you can work out the charges on these. Alright, the next one is what we call a single chain. So this one here is a chain structure. Single chain is our example of this form of silicate. Looking at that. Alright, now, a chain looks like this. We just did our section on polymers. Alright, so here's a chain structure. And as you can see, still based on the single SiO4 tetrahedra, but it's very similar to the structure for a polymer. Okay, so here's the single. Alright, so we bond these just in a single chain. That's how we get this next silicate structure, and that's based on SiO3. What's the charge on it? -2. Alright, so this one over here, I just draw these in a single chain. Matt?
Does it matter which way you got the charge, like the -2 or 2 minus?
You mean up here?
Yeah.
No, it doesn't matter. No, doesn't matter, provided you get the right charge. That's what we're after. Alright, so this is a single chain. An example is dioxide. Well, this is going to have a charge of -2 there. Try to do that a bit neater. -2. So overall, that would be -4. This is +2. This is +2. That's +4. So that's fine. We know it's a chain structure silicate. And this is a formula, as an example of a formula that has got this sort of silicate structure in it. Properties. How do you think this would look if I had a sample of that in front of me? I should have went to get a sample. Yeah, they're all going to be solids, okay? But how would this look? I couldn't go and get a sample of asbestos, unfortunately. But if I had a piece of this stuff in my hand, structurally, how do you think it would look, Jack?
Like a straight line.
Yeah. It'd be like a whole lot of strings all packed together. All right? Asbestos in its raw form is like that. So asbestos has got a similar structure, a straight chain structure. So it'd be like all these long structures packed together. That's what it would look like physically. Okay? As would this one here, all right? This is called a double chain. So I would expect that in terms of properties, if I had a piece of this mineral in my hands, I would probably expect it's going to look something like that. It's going to be fairly fibrous, probably is the word to use. It's going to be like fibrous. Whereas these structures here, they're going to be like one chunk of rock. All right? So it's a bit like a quartz structure, not very easy to break apart. All right? Whereas these ones would be more fibrous. Might be able to get a pocket knife and sort of pry off some of these strands. Okay? Possibly. All right, so we've got single. So here's our single structure here, single tetrahedra. We've got our double. And we've got our chain. Okay? So hopefully you're trying to match these with what's on the board. Okay, over there. And then the next one that I think in terms of complexity is what we call a cyclic, okay, tetrahedra. All right? This one here, the reason why I've actually drawn the circles, someone asked me that before, because when I draw this structure, the circles just help me align things, otherwise you get lost. Okay, so it's way too complex to draw. So this one here is a cyclic silicate structure. So I've got single tetrahedra, double tetrahedra, single chain, double chain, cyclic, and this one here is called a sheet structure. Okay? And we've used that word before when we talked about polymers. We talked about alpha and beta pleated sheets, long, flat structures. We talked about it in graphite as well. Okay? And we'll talk about some properties of that in a minute. This is a cyclic structure then. So all I've done is I've taken, if I had 6, 1, 2, 3, 4, 5, if I had 6 of these in a chain, all I've done is I've just turned them around and formed them into a cyclic structure. That's how I get to 6 in a chain. This one's only got 5 in it, but that's how we got it. No, it depends on how they're all formed. Okay, so all these silicates will be formed in the Earth's crust. Okay, at different temperatures. You would assume that the ones that have got long chains and sheets would have been called fast or slow. No. Slow. Okay. Because what it means is that these silicates have actually had time to align. All right. When we talk, I know we don't go into that anymore. It's not in the course, but in terms of crystalline structures, if you cool crystals down slowly, they become large crystals. Okay. Now it's not directly related to what I just said. All right. But you can see that something that's cooled down slowly is probably going to have a longer chain structure than something that's cooled quickly. If you cool something down quickly, you get small crystals. Okay. Basalt and marble, yeah.
Sorry, not marble, granite.
Granite is the better one. Because granite's got
Very large crystals.
large crystals because it's cooled slowly, okay, under the surface, and basalt
Is cooled very quickly right on the surface.
on the surface from a volcano, okay,
Although
cooled
they both come from
quickly,
through volcanic means, but
cooled at different rates. Yeah. And they're sort of, would they be called as metamorphic, Jack? They're metamorphic rocks?
one's igneous, the other one's metamorphic.
That's right, so they're not really in the same category, but close. All right. All right, so then we had, what did we go through? We've got cyclic, okay. The next one is double chain. Now, this one's a bit complex. So to get to a double chain structure, we would take one of these, chain, and then we put it to a chain again. And we keep on, no we don't, we stop there. 1, 2. What I was trying to show you is that when we draw the structure, okay, there's actually 6 of these. There it is in a cyclic structure. And then there's another 6, another 6, another 6, but it's actually, it's like a zigzagging chain. That's what I'm trying to show down here, alright? So, the double chain structure, if you look at it in the textbook, which is a much better picture than mine, it's actually these things side by side. And when we look at the average of the formula, okay, for these, as you can see, they've taken a slice through the middle of it. They've done something like this. I'm not going to do it accurately. They've done that because it repeats itself, just like this chain repeated itself. This is a way more complex chain because it's got 2 of them. And we end up with a formula Si4O11 minus 6 that you're going to have to learn. Jack.
Is that, it's one top right, is that aluminosilicate?
No. Okay, and I'll explain how to work that out in a minute. Just remind me, okay? So this one up here, alright, silicate structure, yep, and it's got Si, so I'm going to actually block that one off there. That's minus 12. So over here, minus 12 plus 3 plus 6 in total there, okay? And over here, the beryllium is plus 2, I hope. That makes plus 6 overall. They are neutral. They can't cancel one another. Neutral formula. So that's an example there, all right, of a cyclic silicate. Double chain, same deal. I'm looking for this somewhere in the structure. If it's got that formula somewhere in the structure, it is a silicate, and it's based on a double chain, and I know the charge on the double chain because I've learnt that. Okay? These are the ones I think that you need to learn. The others you can work out. But at the end of the day, you need to know them all. Okay? Because we don't know which one they're going to throw at you in the exam. Yes?
Do we need to be able to know how to draw that?
Good question. Good question. All right? Unlikely. All right? The simpler ones, maybe. They could ask you to draw maybe these. Okay? And I'm just trying to think, if you go back on those last 10 years of exams sitting in sector, I don't think they've ever asked people to draw silicate structures. Okay? The only way, alright, the only thing that they would ask you, well, I don't think they'd ask you to draw that, okay? But they have asked you what family of silicate it comes from and given you a formula, and they have given you things like this and said work out the formula. They have done that. Alright? And you'll see that in those past exams. Alright, what do we get up to? Double chain, sheets. Alright, the last one is sheet structures. Now a sheet basically is multiple chains. So if I've got a chain here, to a chain here, and another chain. So if we actually have multiple chains, okay, all the way through, we end up with a sheet structure. And it's continuous. Keeps on going, alright? Indefinitely. And that's why it's called a sheet structure. Now, the example of a sheet structure, and I should have got some of these, okay, here's the start of it, what I was trying to make, alright? So this one here, alright, is part of a sheet structure, and if you can see it, probably can't, but how many silicons is there in a circle here? Actually, this is a double chain, alright? Can you pick a double chain? There's six silicons here, 1, 2, 3, 4, 5, 6. And then there's 1, 2, 3, 4, 5, 6. Okay, if I keep on going with that one, just keep on going, then that's how I transfer a double chain into a sheet structure. Alright? So that's basically the last silicate that we need to look at. Now, the properties of this, I spoke about the properties of a single chain is probably going to be fibrous. This is probably going to be fibrous as well. This one here, well, I've chosen talc as the example of the mineral there. And what do you know about talcum powder? It's powdery. Okay, thanks for that. Alright, if you had talcum powder on your hands, how does it feel? It feels powdery. It feels, would you say it's slippery like graphite? It's talky. Alright, you would say that it's probably fairly slippery. Okay, it is almost like having graphite on your hands. Okay. Graphite is slippery because the layers slide over one another. We know that. We know the structure of graphite. Talc is no different. It's sheets. So it's lots and lots of sheets, okay, of this complex silicate. And in between the sheets there must be what's between those sheets?
Water.
Water? Maybe in some instances, not in this one though. Not bases. What do you think is going to be between the sheets? Well, if it's not the silicate, what must it be? Not oxygen. Metal ions are going to probably be holding those sheets together. Okay? So that's why it's alkyl slippery. Alright? So if you ever have it on the floor, stay away from it. Alright? Just put your foot on it and you're gone. Alright. So again, formula, how do I know? Well, I'm looking for this. But I'm also looking for this because there's two versions of the silicate structure. If I cut that in half, okay, I halve the charge and I halve the silicates as well. So we might see Si2O5 charge on that is going to be -2, okay, in a formula. So again, if I look at that, just grab that one out. That's got to have a charge of -4, okay. The OH has got a charge of -1, -4, -2, total -6, +3, +6, that works. Okay, now, back to Jack's question, okay. How do I know that the structure that I'm working with is not an aluminosilicate? And I just want to get an example, okay, of an aluminosilicate. Alright, if you go to page 329, I've got some examples of aluminosilicate. Okay, and let's have a look at, there's a couple there that aren't easy. I'll pick on the ones, and I'll need to just get rid of part of this here in order to look at the aluminosilicate stuff. Alright, an example of an aluminosilicate given is orthoclase, and it's given this formula here. It's given AlSi3O8 negative. Okay, that's the actual formula of the aluminosilicate, and then it gives us a structure, and it's got KAl Si should be the same, Si3O8 as the formula for this thing called orthoclase. Again, you don't need to know any of these names. Alright, now, based on what we just did, okay, I picked on that one for a reason, because it's one of the simple ones, okay. So, in order to get an aluminosilicate, what we've actually done is something like this. Si2O7, what's the charge on that one? Si2O7, if it was a double. What is it? -6. So if we were to do this, which is a normal silicate structure, like that, okay, and if we were to replace one of the silicons with an aluminium, okay, if we took away one of these silicons, okay, and made it into an aluminium, we've actually formed an aluminosilicate structure. So they're not easy to pick, alright? So we replace the silicon with an aluminium. Now, sorry?
You're in the charge.
I've got to work out, or we are going to work out the charge on this aluminosilicate. This one here, we're told the charge is -1. Okay? -1 is the charge on this aluminosilicate structure. Okay? But going back to Jack's question, how do we know it's not one of the silicates? Well, this one's got aluminium in it up here. So how do I know not to join the aluminium into the silicate part of the structure? Like, do I include it here? Or do I just leave it separate?
It's like a cycle structure, it's got SI6, 18.
Good. Okay, so Matt's on the ball. All right. So we've learnt these. We've learnt SiO4 minus 4. We've learnt Si2O7 minus 6. We've got our SiO3 minus 2. And we've got this one and this one. We've learnt all of these, yeah? They're the ones that we've learnt. So if you've learnt those, if they appear in a structure, okay, unless you've told otherwise, unless you're told it's an aluminosilicate, you would take those as being straight silicate structures. Now, is there any Si3O8s in that? No, it's not. Okay? There's no Si3O8s. So that tells you that the aluminium must then be bonded, okay, as part of the silicate structure. How do I work out that's a -1 charge? Did anybody ask me that yet? No. That's your next question. Okay. How would you work out the charge on that thing to be -1? What are you using to work it out? No, what are you using to work it out? Oxidation numbers. Okay. So, -2, well that's obviously going to be +3. What silicate? Yep, +4. It's a bit of work. Okay, so I've got 3 plus 3. 4 3s are 12. Plus 12. Take 16. Is that right?
Yeah.
It's -1. So we can work out the charge on the silicates by oxidation number. Let's try this one. All right, let's go back. Oh, sorry, back to this one then. So if I gave you this silicate, how do you work out the charge on that? We don't know what the charge is. We're going to work it out. -2, +4, +3, +7. It would be what? It's going to be -7. That would be the charge on that particular silicate. Chat.
So it's an aluminosilicate if the silicate part isn't one of the things.
Not exactly, unfortunately. It's not that simple, all right? And this is why I picked on this one. If you go to page 329, see 329? And it says, an example of an aluminosilicate, AlSiO4 negative. Here's another one, Jack. AlSiO4 negative.
Yes.
All right? And it says an example of an aluminosilicate. It tells me that. All right? The first one we did was that one. Didn't we?
Yes.
All right? Now, if I put this into a formula, and they've given us an example there of this nepheline stuff, okay? They've given us a formula of NaAlSiO4. Okay? Just watch, because this is fairly advanced stuff. So, they've given us that as a formula, but they've told us already that this is an aluminosilicate. Okay? And so, therefore, that means the aluminium is part of the silicate structure. Alright? We'll work out the charge. Because if I do it like this, you'll see that's +1, okay, and the total of that is -1. Alright? But if I do it like NaAlSiO4, if I did it like this, okay, the charge over here is what? This is +3. +1, oops, sorry. This is +3, this is +1. That's got to be -4, doesn't it? Okay. So they still balance, alright? But you have to know, either have to be told that it's an aluminosilicate, and you're hoping that it just simply is one that they don't pick, that it's the same formula. Because if I gave you that, for argument's sake, if I gave you that, and nothing else, I would not expect you to call that an aluminosilicate because it's got SiO4 in it.
So it's just a random gas in the test.
You just hope that they're not going to give you one like that.
So if we do get one, it's a 50-50 chance.
Yeah,
That is terrible.
pretty much. Okay, but there's still a positive thing, because if you look at most of the ones in this aluminosilicate table, most of them don't fit any of these patterns here. They don't fit anything. Okay, so that means you have to read the question very carefully, because if they say this is the formula of an aluminosilicate, boom, sort of. That means you know the aluminium is part of that. So you have to read the question carefully. So I'm pretty sure they're not going to give you a formula like that and ask you, is it a silicate or is it an aluminosilicate? Because the bottom line is, you can't tell. You can't tell. All right?
Are we doing this next lesson?
Yes, I've got to record the next part next lesson. Yes, we will. Got that? Done.